Alright, good morning everybody. We're going to keep working along here with polynomial functions. We've reached 6-3, and from 6-3 we're going to be using long division and synthetic division on polynomials. We've already added and subtracted, we've multiplied them, so all that's left now is dividing. So imagine Doc Brown walks right through that door, hey Marty, 1.21 gigawatts, all that good stuff, and puts you in his DeLorean, takes you all the way back to the year 2005. Wow, such a long time ago. And you're sitting in your grade school class, and all of a sudden that teacher throws a long division problem at you. Were you able to handle it back then? I hope so, because we're going to be dealing with it again now. In order to understand the proper mechanics of long division with polynomials, let's do some long division with just some real numbers like 12 and 277. So just to get some of the terminology out of the way here, remember that 12 was the divisor, and that number that goes underneath that symbol there, that we always called that 277 the dividend. So how did we actually do line division? Let's review that really quick. So the first thing you did is you looked at that 12, and then you just looked at the first, the 2 in the hundreds place there, and you noticed that 12 is too large to be put into 2. So then what you did, you expanded out and you looked at 27. And 12 will go into 27, it'll go in there 2 times. So what did we do with that 2 once we put that 2 up there? Yeah, we multiplied, right? Let's take that 2, multiply it by that 12, giving us 24, and we put that 24 underneath 27. What we did next is we subtracted, right? 27 minus 24, ended up with 3. What do we do next? Well, since 12 was too large to go into 3, same deal as what we had before, we had to bring down that 7, right, and turn that into a 37. Then this process starts over again, right? 12 going into 37 goes in there, what, 3 times, right? So if it's 3 times going in there, what did we do next? Yeah, we just focused on the 3. We took that 3 and we multiplied it by the 12, giving us 36, and then we subtracted, which landed with that 1, and since there weren't any other numbers to bring down, that ended up being our remainder. 23 there was our quotient. So when it came to these problems here, you probably wrote the result kind of like that, with 23 remainder 1. Think of another way we can express that. Instead of saying 23 remainder 1, remember that 1 that's left over is 1 out of that, and it couldn't go into that 12. So we can kind of look at that as a fraction, as 23 and 1/12. Or remember, mixed numbers like 23 and 1/12, really what it's saying is 23 plus an extra 12. And I'd like to focus on the green number, the yellow number, and the red number there. Remember, 23 was the quotient, the 1 was the remainder, and 12 was the divisor. That's going to be key going into long division with polynomials. Let's take a look at that. And let's put these side by side in an epic battle. So let's take 12 divided into 277 just like we did before. Now let's take a look at polynomial long division. What you want to notice here as we go through this is notice all the similarities that this is going to have between the two. So going back over the 12 going into 277, remember we put 12 into 27 and we go in there 2 times. We're going to do the same thing over here, but whenever you do long division, you only focus on the leading term, which turns out to be this x right here, and then you ask yourself, well, how many times can x be put into 2x squared, very similar to the 12 and the 27. Another way of looking at this that makes a little bit more sense now you're dealing with polynomials is we're actually going to take the 2x squared in blue and divide it by the term out there in red, divided by x. We end up with 2x. We're going to write that result right up there. Just like if we were to take 27 divided by 12, we end up with 2 with some stuff left over, right? So back over to the long division with arithmetic, you'd take that 2, you'd multiply it by the 12, and you'd get that 24. Well, we're going to do the same thing here. We're going to take that 2x and multiply it by the x plus 2. We're going to bring that 2 in there now. And now, when we multiply there, we're going to use the distributive property. Bang, just like that. So we took the 2x times the x, we took the 2x times the 2, giving us 4x right there. Now back over to the arithmetic long division. What did we do next? Yeah, we had to subtract. Ended up with 3. We're going to subtract over here, but we got to remember that when we're subtracting 2x squared plus 4x, we're subtracting the entire quantity. So it's very easy to make the mistake here of taking 7x and 4x and trying to call it 11x. No can do. Remember, we're taking 7x and subtracting 4x. So notice what happens with the 2x squareds. The 2x squareds are going to cancel out and add up to 0x squared, which is nice. But then the 7x minus the 4x gives us 3x. So back over to the left side. We brought down that 7 after that. We're going to do the same thing over here. We're going to bring down that plus 7. And then once we were looking at the 37 over here, then this process started over again, right? And we said, okay, 12 goes into 37. It can go in there 3 times. Well, let's do the same thing over here. But instead now we just only focus on the x, and we focus on the first term right there, the 3x. What do we need to multiply x by to get 3x? You got to multiply it by a 3, right? Or you can take just 3x and divide it by x. And then what do we do with the 3 over here on the left? We just took the 3 only, multiplied by the 12, giving us 36. We're going to do the same thing over here. We're going to take just the 3, distributive property with the x plus 2, so 3x plus 6. We're going to jot that down right below the 3x plus 7. Then we're going to subtract, just like we did before. When we subtract, we end up with that remainder of 1. And so earlier, when we were looking at that as 23 plus 1/12, in other words, quotient plus the remainder divided by the divisor, look at how that looks now with a polynomial. We have the quotient plus the remainder divided by the divisor. So take a look at this example here. Once again, we're going to do some long division. And I notice a couple things right now when I look at this problem and when I compare it to the previous work. One thing, if you notice back here when we started off the problem, is that the dividend right there, as well as the divisor right here, they're both in standard form, right? Biggest power, next biggest power, and then the smallest power, and that was true of both cases here. When we look at this example, notice that wasn't the case right here. So whenever you're dealing with a long division problem, you're going to want to rewrite it and put it in standard form. Something else jumps out at me here too. If we take a good look at this and we put this in standard form, we're going to have something that looks like this, right? 3x cubed plus 4x squared plus 10. In other words, we have the cubic term and the squared term, and we definitely have here the 0 degree, but there is no first degree here. It would have been right in there, right? So yesterday I was talking about when you're, I think it was 2 days ago, I was talking about standard form and how you don't need to put placeholders in there where you're 0, and I told you there was a time and place for it. Now's the time for it. Notice how we treated now that cubic polynomial there. We're going to use now 0x here as a placeholder. May seem a little bit out of place right now, but trust me, you're going to be glad it's there when you're doing long division as well as synthetic division. So the first step here, focus only on the leading terms for both, x going into 3x cubed, or in other words, take 3x cubed and divide it by x. Notice here that x will cancel out with one of those x's, leaving you with 3x squared. What happens next? Yeah, we're going to multiply 3x squared times that x minus 2, keeping in mind to do the distributive property. So 3x squared times x gives us 3x cubed. 3x squared times a negative 2 gives us negative 6x squared. What happens next in long division? Yep, subtraction. Remembering to subtract the entire quantity. By the way, nice little landmark to tell you you're doing it right is when you subtract, that leading term will cancel out every single time. It'll add up to 0. If it doesn't add up to 0, you made a wrong turn someplace. Over here, be careful with that subtraction, right? When we're taking that 4 and subtracting a negative 6, we're actually adding 6. So that's why we end up at 10x squared. In long division, what we end up doing next is we end up bringing down that 0x. Now focus your attention here next, because when this process starts over again, now you're going to try and put x into 10x squared, or take 10x squared divided by x. Just knocks that degree down 1, and we have just 10x. Now we bring that 0x back in here, and we bring that minus 2. Now it's time to multiply. We're going to take 10x squared, 10x, and multiply it by that whole thing right there. When we do that, now we have 10x squared minus 20x. Now it's time to subtract. Remember, this will cancel out, and then Ooh, look at that, minus a minus 20, so we're actually going to add 20, x. We'll bring down that 10, process starts over again, 20x divided by x gives us 20. We're going to take that 20, multiply it by x and also by the minus 2. We're going to put it right directly underneath that stuff we just brought down. And then we're going to finish this off with a good subtraction. 10 minus a negative 40 actually bumps it up to 50. So we got a quotient, we got a remainder. We take that divisor, remember we write it in there just like that. It does look awkward, doesn't it? That remainder piece looks a bit strange, but trust me, it's okay to write it like that. So, I'm going to shut up for a few minutes here. I'd like you to try these problems, keeping in mind long division, and work together with your seat partner. And when you guys come back, we'll finish this lesson off with some synthetic division.
But I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts!